Hi PhysCalc, welcome to another video example of U-substitution. So in this video we're going to be talking in particular about U-substitution with trigonometric functions, so sines and cosines. Now we know from our derivative rules, let's just recap, that the integral of sine of x dx is equal to negative cosine of x plus c, because the derivative of negative cosine of x is sine. And we know that the integral of cosine of x dx is equal to sine x plus c, because the derivative of sine x is equal to cosine x. So let's just have these up here. Let's just remember them, because spoiler alert, we're going to need them in the rest of this video. So using that, we know we need U-substitution when we have a composite function. So when these x's have something more going on, it's not just an x, there's another function inside of my sine or cosine. So let's take a look at what happens when I have a function like that. And let's use as an example the integral of 9x squared plus 2 times the sine of 3x cubed plus 2x dx. So there's a lot going on. We have this like polynomial over here. We have this sine function with something inside of the sine function. So there's a lot happening. And because of my embedded sine function, because I'm doing the sine of a more complex polynomial, I have the thought immediately like, oh, I might want to use U-substitution. So with that in mind, remember that U-substitution has the goal of putting this whole thing, this whole integral, into the form integral of f of u du, with the goal of making it solvable, the goal of making it into more basic functions. So to do that, I have these two pieces. This u and this du. So what I need to do is see if there are two things in my function related by derivative. Is there one thing, maybe a u, whose derivative also appears inside my integral? And right away, I'm seeing that I have this 3x squared plus 2x, whose derivative, the derivative of 3x cubed is 9x squared, the derivative of 2x is just 2. So the derivative of that 3x cubed plus 2x is 9x squared plus 2. So I see that right away. So I'm thinking, all right, well, what happens if I make this my u? Does this somehow get related to my du? So let's try that out. So if my u is equal to 3x cubed plus 2x, then f of u, the thing I'm doing to that u, is I'm taking the sine of it. So I'm doing the sine of u, and that's sort of this part right here. So this is all my f of u. The question now is, what is du? And I can find du by looking at du dx. And du dx is equal to d over dx of u, which is equal to d over dx of u, which we just said from over here is 3x cubed plus 2x. The derivative of this is pretty easy. We find that du dx is equal to 9x squared plus 2, just doing the derivative of 3x cubed plus 2x, so the derivative of that. And then if we take my dx and I move it over here, remember it's not quite multiplication, but it's kind of similar, we get that du is equal to 9x squared plus 2 dx. And I just so happen to have a 9x squared plus 2 and a dx, which is awesome. So I can rewrite this function as the integral, just by moving my 9x squared plus 2 dx together, as the integral of sine 3x cubed plus 2x times 9x squared plus 2 dx. And I found that this is my du. I found that this is my f of u. So I'm all set and ready to solve this function, because this is really the integral of sine of u du. And now sine of u is a basic function, so I can take the integral right away. I know the integral of sine is equal to cosine of u plus c. And then because I already know what u is, remember I said all the way up here that u is equal to 3x cubed plus 2x. I can plug that in for my u down here to find that this is equal to the cosine of 3x cubed plus 2x plus c. And that, y'all, is my answer. And that is how we use U-substitution on a trigonometric function. Good luck!